Good morning. Hello, friends. My name is Millicent Malinga, a second year student at African Leadership University in Rwanda. And for this video, I will be sharing my findings and a little bit of calculations and conclusion on probability in genetics. So, what exactly is probability? Well, Merriam-Webster dictionary defines probability as the likelihood of an event occurring. And we have seen probability in a lot of spaces that we live in. The probability of it raining today, the probability of you getting rained on if you go outside, the probability of you getting a head or a tails when you flip a coin. So, probability has a lot of applications in the real world, and in this video, we're going to talk about its application in genetics. But before we dive into that, let's just explain a few concepts that we will use as we go through this problem. Probability itself has been defined as the number of possible outcomes over the number of possible tries. And this can be illustrated by the probability of my birthday occurring in a year. Well, a person can only have one birthday, but how many days are there in a year? 365. So the probability of a day being my birthday is 1 over 365. And we also illustrate this in a game of heads or tails. So in heads or tails, you only have two possible outcomes, a head or a tail. So a head can only occur once in those possible outcomes, and a tail can only occur once in those possible outcomes. So the probability of you getting a head is actually just 1 over 2. Now, this is known as an independent event. An independent event is an event that occurs without depending on the other event's occurrence. And then dependent ones are just like if I went outside today, would I get rained on? That would depend on whether or not it rained outside. So that's the difference between dependent and independent event. And in this situation, we're going to be looking at independent events. This problem that I have was inspired by a show that I love very much called Paternity Court. So what happens in paternity court is where you get men denying paternity because maybe a child has albinism and he claims that in his family there's never been a person who has albinism, so it does not make sense to him why this woman is telling him that he's the father of a child with albinism. So in this situation, I formulated a problem whereby we would have this kind of father who's already had two children with his wife, and now they have a third child who has albinism, and he claims this cannot be my child. And then the court commissions a mathematician like myself and says, well, can you come and help us explain the probability of this happening with, of course, some of this evidence that we've gathered, which is genetic profiling of both the mother and the father. So when they've done this genetic profiling, they come across the fact that the mother and the father both have heterozygous gene for albinism. So I've displayed this on a table, and this is how it would look. So this would probably be the mother, and that would be the father on the side. So we create possible combinations of these people's alleles, and what we get is a child who's homozygous dominant, which means this child would never, at any given point in time, carry the gene to pass on albinism to any one of their children. And then in this situation, we have a child who is a carrier of albinism but will not show it in their skin. And then we have a child who has that as well. And then we have a homozygous recessive, which is a child who carries the albinism gene. And in this situation, the child in question. So now, as we see it, one, two, three of these children actually carry this gene, but two of these children carry this gene but do not display it, so they're known as carriers. And then this child does not carry the gene and does not display it. So out of these four possible outcomes, we have 1 in 4 chances that a child will be born with albinism. And when we come down here, now we're looking at in this situation whereby this couple has already had two children who do not display albinism. What are the odds that their next two children will have albinism? So using the product rule, I actually calculated this, and this would give us a chance of 0.9%. So what this means is that even though the couple already had two children who did not display albinism, they still have children. They still have 25% chance of having children who do display albinism at any given point in time. So every time the wife conceives, she has 25% chance of having a child who has albinism because of their genes. So, in this situation, whereby now the couple is curious, since we already have a child with albinism, what are the odds that our next two children will also be albinos? So, in this situation, every time the woman conceives, she has 25% chance of having a child with albinism. So, in this situation, I created a table that shows the different outcomes. Child one, the probability of having a child without albinism was three quarters, so we placed that there. And for child two, but with child three, we had 25% chance that this child was going to be an albino, and it was actually an albino. And then child four and five are expected to be albino, so we put that probability. Because these are independent events, that means that the probability of child one's existence does not affect child four or five's existence. And now what we are doing is saying these people have child one who does not display albinism, which is three quarters, and then child two's probability, child three's probability, and we are taking these together because we expect these to occur in a sequence. So we're saying child one and two and three and four and five. No albinism, no albinism, no albinism. No albinism 1, no albinism 2, albinism 1, albinism 2, and albinism 3. So when we put these together and calculate, we get that the odds of them having three children with albinism after having two children without albinism would be 0.9%. So what this states is that even though this couple carries the gene to have children with albinism, the chances are really slim compared to having a child without albinism. But this does not dispel the probability that and the chances that they might have children with albinism. In fact, it is possible that this couple could have children who have albinism over and over and over, because every time a child is born and then they conceive again, the probability does not change. So, what we can conclude from this is that probability in genetics is very important because it helps us profile how our children might be born when we combine with people of certain genetics. But at the same time, it does not dispel the fact that these two events that might occur, one could occur way more often than the other. What it does is give us a general idea of how often these two would occur against each other. So in this situation, we can also use genetic profiling, probability in genetics, to check the chances of somebody having cancer due to inheritance and help them put in place measures of prevention. We can also use probability in genetics for a couple that has maybe one person with dwarfism and the other person without dwarfism, for them to understand how likely it is for them to have children with dwarfism. And still, in these situations, we face limitations whereby a couple might face more issues within the child's development that could result in that same thing that probability had told them might not occur very often. In this situation, we might have a cell division error, and even though my husband and I, or my partner and I, have tested and been found to not have the gene to have a Down syndrome child, a cell division error could occur and we can have a child with Down syndrome. At the same time, I can be told that there is no way I have inherited the cancer gene from my parents, but then I could show up with cancer because of the exposure to radioactive material. So, although probability theory might have a lot of applications in the health sector and other parts of the world, it still is only just chance. It just helps us to have a basic idea of, if we were given maybe 1,000 trials, out of these 1,000 trials, how many times would we expect one of these events to occur, and how best can we handle such situations. So they're best for modeling maybe a worst case scenario, but they do not always tell us what exactly is going to happen. I hope you understood and loved the topic just as much as it was interesting to me. Thank you. So, what we were doing in the previous tab was actually using the Punnett square. This is where you are combining alleles from one parent to the other and creating what we call a genotype. So we have a dominant allele A, the one that we were showing for our albinism, and then this is the recessive allele A, small letter A. So this is an online calculator. It's called Omni Calculator, which is used to calculate different genetics genotype problems. So this is the simple Punnett square calculator. We also have the large dihybrid cross Punnett calculator, where it will show, different dominant alleles and different recessive alleles, and see how each child would fare out, how each child's genotypes would look combining these different alleles. So we are just going to use the simple Punnett square calculator as we did in our previous model. So in this situation, we're looking at the mother who has heterozygous dominant, and over here also heterozygous genotype. So, like we had shown in our previous calculation, the chance for them having a child with homozygous recessive that will be showing albinism is 25%. So, we can also try and see what would happen if maybe the mother was actually homozygous dominant. In this situation, the chances of the family having a child with albinism is zero. And if the father had maybe albinism and the mother didn't, the chances of them having children with the homozygous dominant would be zero. The chances of them having a child with homozygous recessive would be zero. So they would have children who are heterozygous and who would be carriers in this situation, like the mother and father we saw in our previous discussion. I hope this helped you a lot, and I will attach the link to this calculator in the report so that whoever is interested in checking it out and playing around with it at some point can do so. Thank you.